Hello everyone. I'm audible in the back? I'm audible there? Okay. Thank you for showing up. This is week 5 discussion. I think the last was the midterm review. I hope you did well on your midterms. The result will be up in some time. Yep. So, just a minute. So me and Zipin are going to take this week's discussion. The first session will be taken by me and the next will be taken by Zipin. I think the homework 4 is already there on Canvas. The deadline is May 11th, and you can sign up for the TA sessions like office hours or one-on-one if you are facing difficulties in any of the previous homeworks or slides or anything. And feel free to post anything on Piazza. Today we will see a problem related to greedy problem and how to approach such a problem. We will go over like how to basically prove a greedy solution, which can be quite tricky sometimes. We will try and solve this problem. So the problem, it goes like this. So there are two N ships. Yeah. Oh, it's not there? Give me a second. Yeah, sure. Just a second. I think the iPad, it gives me a different view of Canvas. Just give me a 1 minute. I think it should be up there now. Once. File discussion. Can you please check again? Yeah, is there? Okay. Yep. So the problem, it goes like this. There are two N ships. So half of them are pirate ships and half of them are merchant ships. And each pirate ship has one cannonball, and that cannonball, it costs around X grams of gunpowder to launch a cannonball X meter from its position. And the one more constraint is, like, each pirate ship can launch exactly one cannonball. Your goal is to basically sink all the N merchant ships by using the minimum number of gunpowder possible. So yeah, uh, is it clear? Or maybe we can go over a practice, a demo kind of thing, an example thing, to better understand this problem statement. So let's say we have a set of pirate ships, uh, and the pirate ships are positioned at 10, 20, and 30, and the merchant ships, they are positioned at 5, 10, and 15. So one possible solution can be like this. So this solution is not necessarily the optimal solution. This is one of the possible mapping that you can do. So one possible mapping is basically destroying this M1 ship with this P1 ship. Oh, sorry. We are destroying the M2 with P1 and P2 with M3, M3 with P2, and then we are destroying merchant ship 1 using a pirate ship 3. So if this is a pairing that we are doing, then the cost would be something like this. It will be the difference of each of the pairs that we have, the difference between their positions, because that is exactly what the gunpowder is. So the solution would be something like this: 10 minus 10, 20 minus 15, and 30 minus 5, and we add them over and we get something like 30. And I think this is not the optimal solution. We can definitely do better than this, but this is one of the possible cases. So I want you to take some time and think about it, like how you would approach this problem. Maybe discuss it with your peers. Let's take a minute and go over it. Anybody wants to try it? Let's try to understand like what exactly we are trying to do here. So we basically have two sets. One set it contains the pirate ships. It starts from P1, P2, and it goes all the way till Pn. And then we have one more set which contains the merchant ships. And we have M1, M2, all the way till Mn merchants. So we are essentially trying to like match each pirate ship with a merchant ship. So for this pirate ship, we have like n number of options, right? For the first pirate ship, it can be done in n number of ways. It can be mapped to n number of ships. Similarly, this P2 can be mapped to n minus 1 number of ships. So you can see the total number of possible ways is n factorial here. If we go and try a brute force approach, then it will take forever to solve it. So let's see if we can come up with some greedy solution that can actually perform better than this. Yeah, so one greedy strategy that sounds correct could be something like this. Let's start with the first pirate ship from the list, like the leftmost pirate ship, and have it sink the nearest possible merchant. May it be on the right or may it be on the left. You just find the nearest possible ship based on the distance and you sink that one. And then you keep doing this for the rest of the ships as well. So if we try this approach for this example, we will get a solution like this. So we are basically choosing P1 to destroy M1, and M2 is being sunk by ship P2. So the distance here will be 70 minus 50 plus 110 minus 100, which is 40. And it seems right here. So that is the trick with actually greedy solution. So if you want to say with certainty like it is true, you need to sit and prove it. And that is the most tricky part here. So do you guys think this is the correct solution? Or can you come up with a counterexample for this strategy? Yeah. Mm-hmm. Okay. You are starting with P1 first. So yeah. So you start with the leftmost pirate ship, and then you sink the closest merchant ship that you have to that particular pirate ship. Actually, I think you are on the right track. So it actually depends on this distance. Let's take this example here. So if we follow the same strategy on this problem, so what we are doing here basically we are moving the merchant ship towards the left of the first pirate ship. So in this case, what will happen? If you look at the pirate ship P1, which one is closer to it? Is it M1 or is it M2? It's M2, right? Because the distance is 20 here, and the distance here is 100. So it will sink this ship. And for P2, there's only one remaining merchant ship that it can destroy, that is M1. So you cannot be picky here, you just have to go and destroy M1 here. So the total cost would be 100 plus 120 minus 200 minus 120, which is basically 100 plus, yeah, which is basically 180. And this actually gives you a better solution here, right, than the 200. So this mapping that we did here, P1 M2 and P2 M1, it is not an optimal one, because you can definitely do better than this. Any other counterexample that you can think of that would like to try here? Is this clear? Yeah. Any other greedy approach that you would like to try? So this time we chose the merchant ship that is closer to the pirate ship. Maybe we can try something like Maybe choose the ship that is farther away from the pirate ship. Maybe that could work. Let's try that. So now we are saying like find a pirate ship and a merchant ship pair that is closest together. Okay, this is interesting. Uh, so pay them and continue. So this is a different greedy approach that I was talking about. So this can also be one of the approaches that you can use to solve it. I don't know if it works or not. And in order to prove that, you basically have to come up with a counterexample, or you have to sit and prove it like it is correct. So what we are doing here, basically, we are choosing a pirate ship and merchant ship pair that is closest together. Pair them and continue with the remaining ships. So if we use this approach, what we are going to do, if we look at this P1, it is most closest to this M1. So we have to pair them together. Similarly, M2 will be paired together with P2. In this case, the total sum would be difference of this plus difference of these two, which is 30 plus 20, 50. Yeah. So the output is basically you're pairing 10 and 40 together and 100 and 120 together. Do you think this approach is correct? Or if you can come up with some counterexample for this one? Let's see the counterexample here. So if we follow the same strategy, then this P1 ship, it will be paired with M2, right? Because that is the closest ship that it has. So it will be paired with M2. And P2 will have to go back to M1. Because you are starting with the leftmost ship. So you are not giving the benefit for the next pirate ship to choose the closest ship to it. So like once you have already solved the ships from 1 to K, the K plus 1 pirate ship, it will only be limited to some particular number of options. So that is actually what you have to think when coming up with this kind of counterexample here. So if you do it like this, the cost will be 20 plus 200, because the difference between these two is 200. So the total will be 220. But can you get a better solution than this approach? So it turns out like you can do better than this. If instead of pairing these things like using this greedy approach, what we can do is we can try and pair P1 and M1 and P2 and M2. So here the difference is 100, here it is 80, total is 180. So 180 is better than the greedy approach. So that's how you are eliminating this greedy approach as well. So having tried two, do you guys have some insight like what could be the right approach for this problem? Yeah?
Make each pirate ship kill the leftmost merchant that is not.
Okay, so you start with the leftmost pirate ship and you destroy the leftmost merchant ship that is available to sink. You're saying? This strategy could work actually. And incidentally, this is what we are going to try now. So this is what we are going to try. Sorry. Yeah. So as you said, like we will choose the leftmost pirate ship and we will try to sink the leftmost merchant ship. So if we try that greedy approach on this problem, what will you get? You will get something like, we will start with P1, M1 is available, M2 is also available. So you will choose the leftmost ship, which is basically M1, so you pair it with M1. Then you go to P2, and then you see like the only available option is M2. So you pair it with this one. So the total cost here is 100 plus 80, 180. And this is exactly what we were getting in the previous example as the optimal solution. So it seems like this should work. But that's the thing with greedy solutions. We cannot be sure until we prove it. So let's see how we can prove it. So as you already know, like the greedy solutions, they have two parts. First one is basically the exchange argument that we have to write, and the second one is the induction that we have to do. So in the exchange argument, what we are going to show that the greedy solution is actually giving you uh, a solution that is at least as good as the optimal solution. Yeah, using the first greedy step that you have decided for your solution. So let's try and prove it. So let PG be the leftmost pirate ship that you have to pair with something, and let MG be the leftmost merchant ship that is available to destroy. Okay. And let P dash and M dash be the arbitrary pirate and the merchant ship. And let's say like this OS is any optimal solution that you can get here. So basically OS is the solution, is the minimum possible sum of the difference of the space that you can get. So it can be any arbitrary solution that you can have. So, and the thing about this OS is like we don't exactly know what this OS is. We just know like it will give you the minimum possible solution. Got it? So yeah, so what we are saying basically, this OS is something which is not doing the thing that we are doing. Like we are pairing the leftmost pirate ship with the leftmost merchant ship, but the solution OS is not doing that. So it is pairing this leftmost pirate ship with some arbitrary merchant ship M prime, and it is pairing this P prime with a most left merchant ship. So now we need to show like there exists a solution OS prime that actually removes this pair that already are there in the OS and add the greedy solution that we have here, right? So we are basically trying to prove like OS prime is equals to OS and remove the pair that it already has and form a pair using a greedy approach. So this is actually what we want to add, right? We want to show like if we add the pair that we are choosing using a greedy strategy, it will give you a solution that is as good as the optimal solution. Yeah. So this is actually what we are trying to prove here in the exchange argument. So these are exactly the terms that we defined earlier. PG is the leftmost ship, MG leftmost pirate ship, MG is the leftmost merchant ship, P prime be any arbitrary pirate ship, and M prime be any arbitrary merchant ship. And as per our greedy choice, this PG MG has to be the one that we are going to pick first to pair. So this is one interesting property that comes out of it. Since we have said like the MG is the leftmost merchant ship, then this has to be true. Similarly, PG is the leftmost pirate ship. That means like any arbitrary pirate ship that you choose, it's going to be on the right of the PG. Yeah, this has to be true as well. And let's define some terms here. Let X be the difference between the leftmost pirate ship and some arbitrary merchant ship. Y be the distance, the absolute difference between P prime, some arbitrary pirate ship, and the leftmost merchant ship. And let distance D be the difference between the position of leftmost merchant ship and some arbitrary merchant there. And this OS actually is pairing this arbitrary pirate ship with the leftmost merchant ship and the leftmost pirate ship with some arbitrary merchant ship. Yeah, that is not in a greedy solution. And let this OS prime basically be the one that is actually choosing the greedy solution for us. So it has to pair this PGMG and this P prime M prime. And we need to show now like this is the optimal solution, like this is better than what OS is doing, or it is exactly equal to the OS. That is what we have to prove. Yeah.
How do you know that P prime and M prime will be paired?
Sorry?
How do you know that P prime and M prime
Will be paired. So it's like this. So let's say OS prime is not picking up your leftmost pirate and leftmost merchant. So you can basically pair this leftmost merchant with some arbitrary P prime, right? Like let's say, so it has to be like that. If it is not paired with MG, then it has to be paired with some other M prime, right? Some other arbitrary merchantship. Similarly, for that leftmost merchantship, you will have to pair it with some arbitrary pirate ship. So we don't know if those two things can be paired together, but we are saying let them be any arbitrary ships. Any arbitrary ships that has to be paired together. So now, if we take these two pairs, if we are swapping these merchants and pirates here and there, we need to show like the new pair, this new two pairs that you are getting, it's actually giving you the solution that is better than the actual OS. That is you are saying here. So this is general, right? You can always pair M prime and P prime because there is no restriction as such, like you cannot pair M prime and P prime, right? Are you getting it? Yeah. Okay. Any other question? So that's the trick with greedy solution. You need to keep track of a lot of variables. Uh, and you will see like these things are going to be very helpful later on. So like we saw this property here, like this note property that we saw here, like P prime has to be greater than leftmost pirate ship and M prime has to be greater than leftmost merchant ship. So how many possible positions can you get for these variables? P prime, PG, M prime, MG? Anyone wants to answer this? So what I'm saying is we have these 4 variables, which is basically PG, P prime, MG, and M prime. So how many different combinations can you have? Yeah? Yep, exactly. So this has to be like 4, 3, 2, 1. 4 factorial, right? Which is, I think it is 24. Right? So it turns out like if we do this ordering of these ships, most of them turns out to be invalid combinations. Like if you take this example, you will see like this P prime is less than PG, but based on our definition, PG has to be the leftmost one, right? So this is not a valid combination. So if you go through all of this, you can see that either P prime is less than PG or M prime is less than MG. So in this one, you can see like the M prime is less than MG, and that is not how we have defined these terms. So it turns out like 18 of these are invalid combinations, and these 6 are the ones that are actually valid ones. Any questions here? Like the different combinations that we are forming? Okay. So now we have 6 cases, and these are exactly the cases that we need to prove. So what we have to do now is, we have this set of 6 possible combinations, and we need to prove like if we do this swapping in these 6 combinations, and it is giving us a solution OS prime, which is at least as good as OS, then we are basically proving our exchange argument. That makes sense? Yeah. So let's see how we are going to do it with case 1. Or anyone wants to try this one, this case 1? How would you go and prove it? Anything? Yeah. So basically, we have this PG paired with M prime and MG paired with P prime, right? This is what is there in the OS. And we need to prove like PG, MG, this is our greedy choice. If you make a choice like this, then we will have to make another choice like M prime and P prime and M prime. And we need to show like this solution is actually better than this one. How would you go and do it? So let's say we are actually making that swapping. So let's see this case 1. Yeah. So the new solution that we are actually having here, what we are going to do is, in OS, we are removing this pair of PG M prime plus P prime MG, and we are adding the one that we are getting from our greedy solution, which is, I think, any doubts here? Like this is how we are forming our OS prime. Now let's try and see like what is the total cost of this whole thing. So let's check this one first. So the distance between PG and M prime, what is it? PG and M prime, it is x, right? PG M prime. The distance of these two is x. So what is the distance between P prime and Mg? So distance between P prime and Mg is basically y here, right? This term. So you are trying to remove this x plus y. So this first term is exactly this. You are removing x plus y here, and you want to add this new pair. So the distance between Pg and Mg, which is basically this one, it is nothing but x minus d. Is that right? Yeah. So this is that term. And similarly, difference between P prime and M prime is this term here, which is nothing but y plus d, which is nothing but this term. And if you solve this equation, you will get something like this. X will be cancelled out, y will be cancelled out, d will also be cancelled out, and you will end up with this equation, which is saying like cost of OS prime is exactly same as cost of OS. Is that clear? Make sense, this one? So now we have to prove it for the next cases as well. Let's try this case 2. So here we are going to do the exact same thing. So this thing, it remains the same, this step. Only thing is like this ordering, it changes. It keeps on changes according to your cases. So in this one, we will get something like this. So I think first half is almost same. In second half, things changes, and you end up with this equation here, plus 2d minus 2 multiplied by x plus y. Okay? And you can see like this term has to be negative. Like this term, it has to be negative. Why? Because this x plus y is greater than d. So actually, these are the things that you need to prove in your greedy solution, and you need to actually show like how this is greater than greater than d. So you can see like when you are adding x and y, this term is getting added twice. Yeah. So another way of looking at it is something like this. Let's say this is A, this is B, this is C. Your D is equals to A plus B plus C, and your x plus y is equals to C plus B plus A plus B, which is nothing but A plus 2B plus C. So in this x plus y, we have this extra B term here. So that's why x plus y has to be greater than D. This makes sense, right? So we can say that this term here, this whole equation, it has to be less than or equal to cost of OS. And this is what we exactly want to prove. Like the cost of OS prime is less than or equal to cost of OS. So case 2 also turns out to be good, right? Let's try it for the case 3. And it turns out like for every case you'll have to do something similar, because this step, it remains the same, only difference is this ordering. Yeah? So whenever you have a problem like this on your homework, and you find out like there can be multiple cases of this approach, you basically have to make this different cases, and you'll have to prove those cases. Okay? So for case 3, This is the pairing. So PG and MG, they are the leftmost, and then P prime is on the right, and M prime is also on the right. So this satisfies the constraint that we have set. So let's see what OS prime is. We are removing these pairs and we are adding these two pairs, and the cost, it turns out to be like this: minus x minus y plus x minus d plus d minus y. And when you solve it, it turns out like x cancels out and not y, d cancels out, and you end up with this term. So here again we are subtracting something from OS, so that's why this has to be less than or equal to cost of OS. So it seems like case 3 is also working. Yeah. Similarly for case 4, you do the similar steps. Now the ordering is something like this. I think we have switched these two terms. Like in case 3 they were the other way around. Now M prime is less than P prime. So if you try and solve this, you will end up with something like this: x cancels out, y cancels out, and you end up with minus 2d. So always you will get some term on, like, in the subtraction part that is actually making it better than the OS. So this has to be less than equal to cost of OS again. I think this was the case 5. So here what we are doing, I think this time we are switching these two ships, merchant ship and pirate ship. So here we will get something like this. So you can see, like, only this negative term it is changing, right? But there's always something in the negative term, or in the best case scenario, or in the worst case scenario, it will be 0, right? You don't remove anything, but you still remain as good as the OS, is exactly equal to that OS. Let's try the last case. So by this time you would have gotten the hang of it. Yeah. So even though this seems like repetitive work, you actually have to sit and prove it, because you might encounter a case which is not as trivial as the other cases. That's why you'll have to go through each and every case. In this one, so now there is M prime between MG and PG. So this is new. So if we try and solve this, so here we can see that there is nothing in the negative term. So this is exactly the same. So if you do this ordering, it turns out like the cost, it doesn't change. Yeah, because everything cancels out here. So in case 6 as well, it is turning out to be true. So that's how we can say like the exchange argument is true. Like in all the cases, it turns out to be true. So now we need to see the induction part. So the part 1 is done. Let's go through the part 2. So there is this definite set of steps that you can always follow to prove this induction. There are, I think, 3 or 4 steps that you have to go through. So it starts like this. So for induction, you need to prove, you need to come up with a base case, right? In induction, you have a base case, you have inductive hypothesis, and then you need to prove it. You come up with some induction, and then you need to prove that induction, right? These are the steps that we have. I think we have already done this in homework 1, the proving the induction part. Something similar we are going to do here as well. So the base case would be n equals to 1. That means there is one pirate ship and one merchant ship. So there is no PNC here, like no combination. There can only be one solution possible, and that has to be the optimal one. So this base case is always going to be true. So now let's define our inductive step. Let's say, suppose that our greedy strategy is optimal for all k less than or equal to n minus 1. Yeah? This is how we are defining our greedy strategy. And let GS, this greedy solution, be the greedy solution for n ships, and let OS be some arbitrary optimal solution. Okay? Are you clear with this term? Like, we have this GS and we have this OS. They make sense to you? So OS is some optimal solution that we have, and GS is the greedy solution that we will get. Okay? Yeah. So by the exchange argument, we have already proved this part. Like the cost of OS prime is always less than cost of OS if our first thing that we pick is based on our greedy strategy. So this thing we have already proved. And based on the definition of OS prime, this pair PG and MG is always going to be part of that solution. Okay? This is what we proved before. This makes sense till now? Now let's go to the next step. So OS prime, the way we defined it was we choose the first greedy strategy. Okay? In the first one, we have this PG and MG, and it will have some other set. And union of these two things will basically be your OS prime. And this T denotes basically the rest of the pairs that you have in OS prime. Okay? Now we are going to use our induction hypothesis here, the thing that we assumed was true for all k less than n equal to n minus 1. So this is what we are using here, the inductive step. So we are saying like this, this cost of gs of n minus 1 is always going to be less than equal to cost of t, because that is what we have in our inductive step. So now it turns out like this first half is basically your exchange argument, and your cost of OS is nothing but pairing this first greedy strategy solution and having some t, union with some other t, the rest of the solutions in that greedy strategy, in that OS prime. And it turns out to be like t is always greater than equal to gs of n minus 1. This is your induction. This is what you define in your inductive step. Yeah. And this is nothing but your the overall greedy solution, because that's how you are doing your solution. Every time you pick the leftmost ship and you choose the leftmost merchant ship, and that's how you do the pairing. So this is nothing but the greedy solution for all the n ships, all the n merchant ships and all the n pirate ships. So this is how we are actually concluding like cost of OS is always greater than or equal to cost of GS. Does this make sense? Any question here? Anything that is not clear? So this is actually a template kind of procedure that you can use for almost all the modify the first step solution. So this can actually, you can do it step by step. Only thing like that will change is like these things. So your definition of OS prime will change, and then then if OS prime changes, then this step will change. Similarly, this step will change. So here you are doing union. It might happen like in some greedy solution you are removing it. So based on that, you actually just change your OS prime, and more or less this overall procedure, it remains the same. Okay? So now that we have proved this whole greedy approach, now let's try and solve it. So anyone wants to like tell me their strategy, like how they are going to implement this one? You choose the leftmost pirate ship, and then you choose the leftmost merchant ship, and then you pair them together. Then you go to the next pirate ship, and you again perform the same step. So how can you implement it? Any ideas? Yeah? Okay. So you're saying we can first sort it, then? So you will sort pirate's ship differently and the merchant ship differently? Okay. That makes sense. And then you do one-on-one mapping? I think that should work. So yeah. So you basically need, as you said, you need to sort it in the increasing order, or at least non-decreasing fashion. Similarly, for merchant ship, you'll have to order them in increasing order or non-decreasing fashion. Then you pair them together. You choose the first element from pirate list, and then you choose the first element from merchant list. You make a pair and you add it to the output. Similarly, you go for the next index, I equals to 2, then go for I equals to 3, and you cover all the ships. And then you simply return the output. What is the runtime of this? Yeah? Anyone? Yeah? So n log n for sorting. Yeah, and this iteration will take n. This is nothing but big O of n log n. Yep. So this is it. So this is how we have actually solved this problem. If you have any questions that the strategy that we went through, if you have any doubt or anything, you can ask me the question. Anything that wasn't clear, any step, like if you are faced with some other greedy approach, like a greedy solution that you are trying to prove, and you think like something can be a bottleneck that you haven't understood, feel free to ask. So this is a big improvement, right? This n log n is a big improvement, because initially we were having this n factorial, big O of n factorial, not big. It's not big O. I think it was big omega. Yeah, and from this we are reaching to this big O of n log n. It's a very big improvement. Yeah. So the greedy solutions, they always look and sound correct until you come up with a counterexample or you prove them. So we have 3 more minutes. Maybe I can give you a problem statement that you guys can think over this weekend. Maybe, if you want. Yeah. Just think about it, and if you have any doubts, we can discuss about it later, or I can post the solution on Piazza. Let's do it. It's so that you don't forget what you actually learned here. It's nothing. So it's just a bonus kind of thing that you can try later on. Yeah. So the problem, it goes like this. So we have n oxen, ox1 to oxn, and each oxen has a rating of s of I, and you need to pair these oxens up in a team so that this condition is true. So this p is basically a constant that will be given to you, and you need to find this pairs. You need to maximize this pairs such that the sum of Si and sum of Si and Sj is greater than or equal to p. And one oxen can be a part of at most one team. You cannot pair the same ox in some other team. Okay, if it's part of a team A, it cannot be part of team B. So your goal is basically to maximize the number of teams or number of pairs. It's almost similar to the problem that we did before. Anyone has a solution for that? Yeah? Okay, yeah, that is one approach. So the approach is basically we sort the whole list. We use 2 pointers, one at the start point, one at the end point, and we then keep on decreasing them. Yeah?
If you find a pair, then if you find a pair, then decrease it.
Okay.
If you don't, then only one.
Okay, let's say your first pointer is I, the last pointer is j. So you try and do Si plus Sj. If it is less than p, then you basically increment your I. You are saying? Yeah. And if it is not, then you got the solution, right? So that means you have to increment I anyways, and then but decrement your j as well, right? Now you have to prove this approach actually. So that was actually interesting, since you come up with the solution in the first go. It might not happen like you get your solution in the first go. So you'll have to come up with a counterexample for that. Okay? So try this problem, it could be fun, and you will actually retain the information that we went through in this lecture. And if any doubt comes up, then you can always come to the office hours or post it on Piazza. Okay? Thank you for showing up. All the best. Here for a couple of minutes. If you have any questions or doubt, you can ask me.